So welcome to Redox and Electrode Potentials, determining the feasibility of reactions using electrode potentials. All right, okay, still in my pajamas as asked by my students. Okay, now redox and electrode potentials, feasibilities, we're going to look at lots of different types of reactions, so very, very important. If we look here, we've got a hydrogen electrode. Hydrogen electrode is next to a normal electrode, a copper in that instance. Okay, and remember whatever comes on there is the value of the other one because this is set to 0. Okay, now just reminding you, okay, the element with the most positive cell potential gains the electrons. Okay, so in this case, the copper would gain the electrons because it's plus 0.34, and this would lose. And the one that loses is always on the left. So this is the anode, always loses, and this is the cathode, always gains. And this is the negative electrode because it loses lots of electrons there. All electrons flowing around, too many electrons, so therefore overall it's negative. And then this sucks in the electrons. So basically there's not enough electrons, which means that's positive. Okay, remember, electrons are negative. Okay, the simplest way I can put it is if the most positive cell gains the electrons, it makes sense because it's most positive and it gains the electrons because they're negative. Okay, now calculating the E cell, the overall electrode potential between the two, is just the cathode minus the anode, or in easier words, the most positive one minus the most negative one. And that can be used in exams. We've got an exam style questions video on this as well, which is well worth a watch. Okay, now drawing cells. There's 3 types, and then we're just going to go through those 3 types. We went through it in the last video, but well worth going through again. So the most normal type is this one, where you've got, remember, your mark for your salt bridge, mark for your voltmeter, mark for your solutions, mark for saying what's in the solution. Okay, mark for the different conditions or for gas pressure, temperature, concentration, all of those really, really important. Okay, and as I said before, this is the anode on the left and the cathode on the right. And this is just the example if you've got a metal as a conductor. So the metal as the conductor becomes the electrode. Okay. Now the overall E cell is in the voltmeter in this one. Right, let's go to the next one where you have solutions. So the other electrode involves a redox equation, for example, where you don't have a solid, okay, then you might use a platinum electrode. Okay, still got your salt bridge here, still got your voltmeter, still got your other solution. So if you look here, we have that. So we've got manganate and H+. So if you're saying what's in there, you have to write down manganate and H+. Okay, so, and then on the other one, we've got the most negative on the left, the one that's going to lose electrons, the most positive on the right, the one that's going to gain electrons. So it's really important, if you have things that are solutions like this, you can't just do a normal electrode, you've got to do a platinum electrode if you are drawing it. Right, next and last one, okay, is non-conductors. Okay, so if we have a non-conductor, typically gases and things like that, covalent gases, we use a platinum electrode too, but we need to have this set up so we can pump the gas in, you see, much like the hydrogen electrode. And again, the most positive one is on the right, is the cathode, and the most negative one is on the left. And we can see that losing electrons here because it's the most negative, gaining electrons here because it's the most positive. Okay, so we've got 2 setups. And again, our salt bridge, our conditions underneath, and then a lovely voltmeter at the top. Okay, so there's our 3 types of drawings that we might do. If you want to look at me doing one drawing, just as for your exam, it's in the video before this, which says about drawing these things. Okay, and that is usually a 4-mark question in the exam. But today we're going to talk about something else. So this is the bit that people find really very difficult. So you're normally in the exam given a list. So we've got this reaction here, chlorine plus 2 bromide ions, but they can give you a list like this, see a big list, and they can ask you to select different parts out of it. Now, we've already selected the chlorine and the bromide. Okay, so the bromide is there and the chloride is there. Notice, as we've said in other videos, it's always written as reduction gaining of electrons. We're given cell potentials, okay, but we're going to work out what's happening and why it's happening in this reaction here. So let's highlight the bits we need. So we've got that. And let's remove everything we don't. Okay, so we don't need that. Now, this is something called the anti-clockwise rule. I don't really use the anti-clockwise rule in lesson. And the reason is, I think if you tell people how to do it normally, they don't really need to do this. But I'm going to show it to you just in case that is helpful towards you. So what you do is you put on the top the one that is losing electrons, and that's the least positive, most negative. That's the one that's losing, and the one that's most positive gains the electrons, okay? So the most positive is always written at the bottom, and then you just do it anti-clockwise like this. And that means that this top reaction is going to lose electrons, and this bottom one is going to gain electrons. So what I do in class is just say, look, the most positive gains, and the most negative loses. So you've got to flip the one that is the least positive. Okay, but this is a nice picture away, the anti-clockwise rule to say. So that means the most positive stays the way it is because it's gaining electrons, and then we've got to flip the other one, okay? So the equilibrium is to the left on this one because it's losing electrons, and the equilibrium is to the right because we're gaining electrons on the bottom. So when you're doing questions about this, they want you to talk about the equilibrium being to the left or the right. And because it's always written as reduction, you need to refer to it as the left or the right when you're referring to the reduction half equation, as in written like this, gaining electrons all the time. So if I say the equilibrium is to the left, I'm stating that it's losing electrons. If the equilibrium is to the right, it's gaining electrons. Now, if you want to go into a bit more detail, the more positive gains electrons and therefore is an oxidizing agent, makes something else lose, and the other one would be a reducing agent. Okay, and that is how you do it, and you can combine that into this full equation here. So if you look here, what's happened is we have flipped this. We're saying Br minus, starting with Br minus, going to Br2. So there's your Br minus, and it's going to Br2. And we're making the chlorine gain. So we have to start at the chlorine, there's the chlorine, and go to the chloride. And then the electrons have cancelled to create this overall equation. So that's how you might have one halogen reacting with another halogen, okay, and one causing another to be oxidized. So one being reduced and one being oxidized, and you have a redox reaction using halogens, and it's normally called displacement. So we're now going to talk about the feasibility of reactions of these non-metals. So that means you're given two different ones, and you said, right, okay, is this going to react or not? Is it feasible or not? Okay, and I would normally write the full equation if it's going to work. Now we need to decide whether it's going to work or not, okay? So if we're looking at this, we have got our reduction. So this is our reduction here. And I'm going to get rid of the one I don't need, so I don't need fluoride. Okay, and then I'm going to go for this. Okay, so if this is the case, I need to look at the different ones. So iodide is here. Okay, and the iodide ions is 0.54. So the one that's including iodide is 0.54. Okay, now for the one underneath, iodine is also in that one, so it's 0.54. So we just write the one underneath as well. Okay, so it's 0.54. The bromine is underneath, okay, which is 1.07. Okay, so let's write 1.07. And then the chloride is underneath, 1.36. Okay, so that is 1.36. Okay, so we've got our numbers. Now, all we have to do now is just decide which one is the most positive, right? So the most positive one on this side is this. That's the most positive. And then the most positive side on this side is this. Okay, so we know that this one means it's going to gain E minus, okay, and this one is also going to gain E minus. Okay, so it's got that. So that means it needs to be written in that way. So that basically means iodide, for iodide to react, the equilibrium has to go that way. It has to go there to the left. It has to lose electrons. So iodide has to lose electrons. Well, in this one, the iodide is going to lose E minus, right? Okay, so basically that's going to work. So iodide is going to lose, and that means the bromine will gain. So what we do is join these two up, okay, and we can say, right, okay, Br2 plus 2 iodide. Okay, so there's 2 iodide here. Okay, 2 iodide there. So we flipped this one. This is going in this direction, and the bromine is going the other direction. Okay, and because we're being good here, right? Okay, let's just put our 2 electrons in as well. Okay, so we've got our two electrons. Those two electrons are from the bromide, because the bromide's going to gain it. Right. Always put a reversible reaction in. Okay, because it's all reversible reactions down there. Okay, and then from that, the bromide is going to turn into 2Br minus, and we can see it's the bromine, sorry, is going to change into 2Br minus, which you can see there. Okay, and then the iodide, you can see iodide is going to go into I2. That's I2, and I haven't written the state symbols just because I haven't got a lot of space. Okay, but I would if I was you, I'd write the state symbols. Okay, now if that's the case, if you're going from bromine plus 2 electrons, and then 2I minus to I2 is plus 2 electrons. So basically we have 2 electrons on each side, which means that the 2 electrons on each side are going to cancel out. And that gives us our full equation, which is Br2 plus 2I minus goes to 2Br minus plus I2. Now, if we look at the other one, the iodine is 0.54. So the iodine this time is going to, it's the lower number, so it's going to lose E minus. This is going to gain E minus. So let's see again whether it works. So the chloride must gain. Now chloride can only lose. Okay, can you see it? It only loses. If you start from chloride here, going in that direction, so it has to go in that direction to react. Chloride therefore loses. Okay. So if chloride therefore loses, okay, it will lose and not gain, and we want it to gain. So let's go through that again, because I don't think I said that as clear as I could have done. The chloride has to go that way and has to lose. In this reaction, it's the most positive, so it wants to gain. It can't. Okay? If we then go for the iodine at this point, okay, the iodine, okay, well, the iodine can only gain, because the iodine, when it reacts, gains 2 electrons. This setup says that it has to lose. Okay, so basically this does not work. Okay, so we've got one that does work and one that doesn't work. And we've got the equation for one and the equation for the other. I hope that helps. These are the kind of things that you're going to have to get used to. Okay, seeing whether something works or not, writing the full balance equation, deciding whether it's feasible, this is not feasible, or whether it is feasible, and if it is feasible, write the equation. So let's go through a few examples of what we did just there, just with these species, and they're all done as reduction. Okay, and let's go for our first one, which is iodine plus zinc. We just need to decide whether it is feasible or not, and please stop the video and do it yourself. So first of all, we need to find out where they are. So iodine is down here, and that means iodine can only gain electrons. The zinc is on the right, and that means equilibrium will be to the left on this one. It can only lose electrons. So do the numbers fit that? Minus 0.76 and plus 0.54. Well, that's the more positive, so it will gain, and that's the more negative, so it will gain. So we'll lose, sorry. So this will lose. Okay, which means basically we can write zinc 2 plus, okay, and we can put that as aqueous plus 2I minus, okay. Okay, and that can be aqueous as well. Okay, so all we've done is taken it and put it over there, and there's 2 electrons there and there's 2 electrons there, so they have cancelled. So then we just calculate the standard potential, so that basically means we've got the E cell, okay, or something like that, and that is 0.54, the most positive minus the most negative, okay, and 2 minuses are positive, which means 1.3. Okay, and there we go. And we've done our overall cell potential, and we figured out whether it's going to react or not, and it does. This is totally feasible. So if you're in the exam, you have to write down, this is feasible, okay? And there you go. Okay, so our next one, we've written it out for you this time, okay? And you can see, I'm just going to show you how we got to this point. We have got to this point because we start with bromine, and we started with copper. So bromine can only gain, can't do anything else. Okay, and then the copper can only lose. So bromine is 1.07, and so therefore it will gain, even though it can only gain because that's the direction of the equation. It will gain because it's the most positive cell potential. This one is the most negative, 0.34, and therefore it will lose. So all we did is take what copper turns into, copper 2 plus, and what bromine turns into, and we put them as our products. Okay. We then cancelled out the electrons because there's 2 electrons in each one, and they're cancelled. And then we did 1.07 minus 0.3 for most positive minus most negative. And that's how you do your cell potential.